now. Dr. Banerjee.
Yeah, hi, welcome everyone to this IISS webinar. We do webinar every month almost. There are some exceptions, but I want to thank all of you to joining today's call. And I want to specially thanks Dr. Ambuj Tewari for doing this. And I'm handing it over to Himel. He's going to talk a little bit about what IISA is. Thank you.
All right, thanks everyone for joining. So we have some introductory slides about IISA, International Indian Statistical Association. I think most of you are aware that IISA is an organization that the objective of IISA is to promote education, research, and application of statistics and probability throughout the world, with a special emphasis on the Indian subcontinent. The goals of IISA organization in general are multi-factorial. So you can see to foster collaboration for the development of statistical science, to serve the needs of young statisticians, and also encourage cooperative efforts between industry, academia, government, and business, really to make sure there is cross-pollination of ideas and statistical development across different sectors. So there are several events that IISA does, and one of the main events is usually the annual conference. For this year, 2024, it's happening in December. Most of the registration deadline is, of course, over now, but there are really interesting invited sessions, contributor sessions, as well as some short courses. As you can see, the short course here, Omics Data Science and Interpretable and Interactive Machine Learning. So this year, this is happening in Kochi, Cochin University of Science and Technology in Kerala, India, December 27 to 31, 2024. And I think there is another conference coming up in summer 2025, which is happening in Nebraska, Lincoln. I don't know the exact dates, but sometime in May, Dr. Banerjee might be able to tell that. Okay, and for the student body particularly, we have the student paper and poster competition that's part of the IISA conferences. It usually two student paper categories are awarded. One is in the theory and probability, and one in the applications. Also, student poster competition happens in the same conferences every IISA conference. So these are really opportunities for students to get engaged and share your research with the broader IISA community. We also have Early Career Award in Statistics and Data Science in 3 categories: theory, application, interdisciplinary studies, and practice. And Dr. Tewari, who is our speaker today, was the 2023 winner in the interdisciplinary studies and practice category. And the goal of this slide deck is to really encourage people to join the IISA membership. Especially for students, it's actually free, up to 4 years. Proof of student status is required. But for others, it's pretty reasonable price to join IISA given all the activities that IISA does throughout the year. I think that's the end of the slide deck. And I will now encourage Dr. Tewari to share your slides. So in the meantime, I will introduce the speaker. So Dr. Tewari is a professor and director of the master's program in data science at the Department of Statistics and Department of EECS. I'm assuming that's electrical engineering and computer science at the University of Michigan. Dr. Tewari's primary research area is machine learning, as you can see from the title talk. His work spans the mathematical foundation of machine learning algorithms, as well as discovering new application areas for machine learning. Recently, his research has focused on topics such as statistical learning theory, online learning, bandit problems, reinforcement learning, high-dimensional statistics, and large-scale learning optimization. From the application side, he is also applying machine learning to problems in behavioral sciences, computational chemistry, computational biology, learning sciences, and complex networks. So I would like to thank Dr. Tewari for being a speaker in this webinar. We have really great number of registrants, which is the highest so far in the IISA webinar that we have conducted. And I would hand it over to Dr. Tewari.
Thank you so much, Emil, for that kind introduction. Thanks also to Hia and Kaushik and all the ISA folks who run this webinar series. I really appreciate the invitation. The QR code here is for the participants. You can point your phone at it, and that will take you to a copy of the slides. And I think one of the panelists might also post a direct link on the chat. So it's just amazing to be here. I hope you all can hear me okay and see my slides. I think the immense amount of interest in this topic, we can see there are over 100 participants in this webinar, is because it has affected everyone, right? I think when the original Transformers paper was published, and it's hard to believe it's only been 7 years. So the first reference on this slide is Vaswani et al. 2017. Attention is all you need. Now it has this legendary status in the field. It introduced the transformer architecture, and the title says attention is all you need. That actually reflects what was happening before this paper, is that attention, and I'll explain what attention means later, it was used as an add-on to other architectures, especially recurrent neural network architectures. And it was always thought that, oh, we add attention to the architectures to make these architectures work better. And this paper said attention is all you need, right? So you can actually build entire natural language processing systems by only stacking attention layers on top of each other. And that really unleashed a revolution. And some highlights of this revolution are BERT was released in 2018. It established this now dominant paradigm that you pre-train a model on web scale data, and then you fine-tune it on all sorts of downstream tasks. And the famous GPT series of models, they started in 2018. GPT-1 was released. 2019, GPT-2 was released. And then 2020, GPT-3 happened. By 22, OpenAI had released ChatGPT. And that's where LLMs burst into public consciousness, right? And we've been seeing lots of interesting developments in the space. And the space also has become a little bit closed. So you can find papers on GPT-1, 2, and 3, but the GPT-4 paper is not a real paper. It's only like a condensed sort of report, and OpenAI did not release the full details. So nobody really knows how many parameters it has. GPT-3 had 175 billion parameters, so we can assume safely that GPT-4 only had more, maybe even 1 trillion parameters. And these models keep getting larger, and as they keep getting larger, they become better at various tasks. Initial models were not very good at logical reasoning, but they got better. They still make mistakes, they still hallucinate, and I'll talk a little bit about it at the end. But I think no one will deny that there has been an absolute revolution. And it's the interesting thing for a broad audience like this is that if it was just something happening in natural language, maybe you wouldn't care. But my point is that it's actually much bigger than that. And it'll take us a few years to fully realize the impact of this revolution, because what's happening is that transformer-based models are also making an impact on fields outside of natural language processing. So they are actually very good at vision. With the vision transformer paper was released in 2020. And even though transformer was built for a modeling language, it actually is very effective on vision tasks. It's very effective on molecular tasks. And the Nobel Prize, as I'm sure you saw the announcement earlier this year, the Nobel Prize in Chemistry in 2024 this year was awarded to 3 people. 2 of them were part of the AlphaFold team. And the AlphaFold system also uses the transformer architecture in a very central way. And a competing model from Meta called ESM4 also uses transformers in a very central way. So transformer is starting to appear like a very general architecture for detecting patterns across a variety of data types, whether it is language or vision or molecules. Okay, so that's where we are today. But in this talk, I don't want to go from 2017 onwards. Okay, so the goal of this talk is not to take you to the cutting edge of research. The goal of this talk is actually look back at the history. How did we arrive at the moment in 2017? So that hopefully after this talk, you can communicate with a friend, with a colleague effectively about transformers, and the jargon used in this field doesn't prevent you. Because there's a big barrier, because most of this work is happening in machine learning conferences, in computer science conferences. So every field has its jargon, and sometimes it can create barriers. When you open a paper that uses transformers and NLP, you will see words like, oh, we have a language modeling head. Oh, we have an embedding layer. Perplexity of our model is 109. So things like that. We did layer normalization, right? They use all this jargon, and it sometimes can hide the sort of the basic simplicity of the transformer architecture. And I did not know anything about it up until about 1.5 years ago, when students in my introduction to deep learning class, when I was teaching this class in winter 23, GPT had been released, ChatGPT had been released, and they were just really, really interested in knowing more about the architecture. It was not on my syllabus. So when I taught the deep learning course again in 2024, I did include a module on transformers. And teaching to undergrads, I hope, has helped me understand where the sort of trouble points tend to exist when you introduce this topic. So I hope I can use that knowledge acquired, and I thank my students in my deep learning class and in my graduate level LLMs and transformers class this semester for helping me refine my approach to how I teach these things. So I was given about 40 minutes because we'll also have about 10 minutes of questions at the end. So I'll just spend about 10 minutes each on 4 major topics. What do we mean by language modeling in the context of large language models? What are word embeddings? How do they enable neural language models? And from neural language models, how did we come to these very large scale language models? What's the role of self-attention? Okay. And perhaps the 4th part is the key one. And if I can get across what self-attention does to the input, I will consider this talk a success. I also want to point out that the perspective I take, which is very rooted in statistical modeling and it's a historical approach, that's not the only way to approach LLMs. And for another perspective, I highly recommend Sasha Rush's excellent tutorial. Sasha is a leading researcher in NLP, in natural language processing, and there's a link from my slides to his excellent talk, LLMs and 5 formulas. That takes a slightly different perspective. Okay, so what do we mean by language modeling? And this should really, really delight a statistical audience, because the way language modeling is done, it takes a very statistical, very prediction-oriented view of things, right? So if you consider a sentence like, I withdrew some money from the blank, as a speaker of English, you immediately know that likely completions of this sentence include words like bank, ATM, account, whereas words like restaurant, cafe, and food are unlikely completions, right? So somehow, because we've been exposed to a lot of English sentences, we know what's coming. We have a good idea of what's coming. And of course, we don't have to do it at the word level. We can do it at a character level. So if I say, I am TALKIN blank, you know with almost certainty that the missing letter is G, right? Because you're aware of English vocabulary and you know that TALKING is a valid English word. And this is something, these statistical regularities are used in autocorrect and word complete software that we use in our sort of keyboards on our phones and when we write emails and when we search on Google. Because of these regularities, we have things like autocomplete. But the interesting thing to point out is that this is not really new. This is a very old idea, goes all the way back to the founding father of information theory, Shannon, who was actually born in Michigan, and he did his undergrad at Michigan before going to MIT. So this is an abstract of a paper he wrote, famous paper in 1950, Prediction and Entropy of Printed English, where I have highlighted the part where he says that prediction of the next letter when the preceding text is known, that's a key prediction task to capture regularities. Okay, so this is already in 1950, Shannon's talking about, let's predict the next letter when we are given the previous few letters. And in fact, he defined a game with human subjects where they would see prefixes and try to guess the next letter. And he used their performance to estimate how much entropy there is in English. And his estimate was between 0.6 and 1.3 bits per character. And this estimate has stood the test of time. I think the more refined estimates these days tend to be closer to the upper limit than the lower limit. So language modeling really just means I'm going to build a probabilistic model. I'll assign probabilities to sequence of words. And this might seem like a very natural idea. If you're trained in statistics and probability, that's sure, I'm going to put a probabilistic model on language. It's very controversial. It's hard to imagine that this can be controversial because now we take LLMs for granted. But linguistics has been dominated by the Chomsky paradigm, right? Where you take a non-probabilistic view of language and you say that there are grammars and there are various hierarchies of grammars. There are regular grammars, there are context-free grammars, there are context-sensitive grammars, and there are fully recursive grammars. And Chomsky is famous for having said that the concept of a probability of a sentence is meaningless because a sentence is either grammatical or not grammatical. So what do you mean by a probability of the sentence? Of course, what we mean by the probability of a sentence is how likely is that sentence to appear in some big corpus like the web, right? So that's the perspective we will take. And by chain rule, we can write down the probability of any sequence of words as a product of these probabilities over here, probability of the first word, and then the probability of the second word given the first word, and so on and so forth, right? So this is just chain rule. Nothing deep is happening here, right, yet. But it's already interesting because if you think about the probability of a sentence like I am talking, now this probability can be modeled as probability that it starts with the word I, and then the word am follows the word I, and then the word talking follows the word I and am. Where can we get these probabilities? If we go on the web and we just start collecting data, unsupervised data, nobody needs to label it. I can just look at how many times I am occurs on the web. And out of those occurrences, how many times did talking was the third word? And that gives me an estimate of this last probability, right? So I can estimate these probabilities from just large databases of text. Now, the key assumption that the early literature made was that we're not going to model the dependence arbitrarily far back into the future. We're going to make a classic assumption, Markov assumption, very familiar to a statistical audience. We'll just say that the probability of Wn given the past only depends on the last n minus words, n minus 1 words, okay? So I'm only looking at n grams. And n gram in natural language processing is just a sequence of n words, right? So I look at an n gram and I say, how do the past n minus 1 words affect, what's the conditional probability of the nth word given the previous n minus 1 words? Okay, so if n is 1, that's just a unigram model. You're just drawing words independently from their overall distribution. So that doesn't generate very interesting English-looking text. N equals 2 gets a little bit more interesting. A bigram model at least looks at the previous word. N equals 3 gets more interesting. You look at the previous 2 words, and so on and so forth. And now you might say, well, isn't the problem solved? I'll just use a large enough look back window, a large enough order for my Markov model, and maybe that's enough to capture regularities in language. Now, the problem is vocabulary size, okay, which is kind of the state space of the underlying Markov chain is really large. It's the order of the vocabulary. And vocabulary of languages like English, they tend to be in the 10 to the power 5 range, right? 100,000 words is easily the size of a sort of a vocabulary in any sort of general purpose use case of English. And so the number of probabilities you have to estimate is of the order of V, the vocabulary size, raised to the n, the Markov window you're using. So if V is 10 to the power 5, already at n equals to 5 or 6, you're hosed, right? You just cannot estimate these many independent parameters. And that's kind of the point. Like, we do not want to estimate these different conditional probability with no structure, okay? And that's where sort of these word embeddings and neural models will come in. But classic work just did this very simple, let's just estimate one probability for each of the V to the power n possibilities. And that's really hard to go beyond 4 or 5 grams, right? And n gram where n is either 4 or 5. One key thing to realize here, and this will remain relevant in more modern architectures, is that as soon as you have this kind of conditional model of the next word given previous words, it's not just a model of language, it actually is a generative model. You can generate text from your model. Because what you can do is you can sample the first n minus 1 words and say, well, what's the probability of the nth word? Just sample a word with that probability. Now you have n words. Now you move your window. You look at the most recent n minus 1 word. So from 2 to n, you plug it in your model. The model gives you the probability of the next word. You sample that word. And so you can just fill in the sentence by you can generate a sentence by filling iteratively one word at a time using your model. Okay, and this is called autoregressive modeling because, autoregressive models, as we use them in econometrics and statistics, they have the same idea that you can use the past k instances to model the probability of the next one. Oftentimes, autoregressive models are linear. Here, we will use neural networks, so nothing will be linear, but still the idea is using the last few things to get the probability of the next token or word, okay? And as you increase the order of these Markov models, they do get better. And this is a screenshot from Shannon's famous 1948 paper that founded the field of information theory. And you can see that the top text doesn't really mean anything even locally. It's just as a unigram model, so you're drawing words independently. Representing and speedily is an good app, which really doesn't make any sense. As you go to second order, so if you use a bigram model, then at least locally it starts to make sense. The head and in frontal attack on an English writer. So still the sentence is not making global sense, but it's making some local sense. Like locally you can see structures that And it gets better and better as you go to 4 and 5, but then you sort of hit this ceiling that you can't do the estimation properly because vocabulary is large and n is also large. There were a couple of problems with these early models, these n-gram models. Number one problem is they don't do a very good job when they encounter words that are similar in meaning to what they saw in the training set. Okay, so that's the number one problem that had to be solved. How do you capture some aspect of the semantics, the meaning of words? And word embeddings are a solution to that problem. So we'll spend a few minutes looking at word embeddings. And the second problem is because you're restricted to a very small n, you are not doing a good job with long-term dependencies. And natural language has arbitrarily long dependencies, and we'll see some examples later. Okay, and so the self-attention architecture will be a solution of this problem of how do you model very long-term dependencies while not incurring a huge blow up in the number of parameters in your model. Okay, so this is why these two ingredients are central, because original models had these two problems, and the meaning problem is solved by word embeddings, and this long context problem is solved by having this self-attention architecture. Now, before I move on to word embeddings, just one point about evaluation. And this is because if you open these papers, you will often see perplexity as a evaluation metric that's reported in papers. So I just wanted to spend just 2 slides on evaluation and perplexity. So in general, when you build a language model, you can evaluate it in qualitatively 2 distinct ways. If this language model is a part of a larger system, maybe it's part of an automatic speech recognition system, maybe it's part of a machine translation system, and let's say, suppose your engineers have built, you're a company and your engineers have built language model A and language model B, and you're trying to assess which one's better. Well, you can build 2 prototypes of your system where you put in LLM A in the first one and LLM B in the second one, and then you evaluate the whole system end to end according to some sort of end metric, which is going to be a machine translation metric if you're building a machine translation system. It's going to be a speech recognition accuracy metric if you're building an automated speech recognition system. And you say, well, whichever one gives me a better overall system is the better language model. Now, this is great because it is aligned with your real world use case, but it is bad because it is very time consuming and very expensive. You have to build the whole system, evaluate it before you get a sense of how A and B compare with each other. That's why a lot of people are interested in intrinsic evaluation, which is if I trained a model on some text corpus, I can always set aside 10%, some small fraction of that test corpus, separate as a test set, and I can see what kinds of probabilities does my language model assign to unseen text. And if it has picked up genuine regularities, it should say that these real sentences that I hid from the model, it should assign them relatively high probabilities. And that's where perplexity comes in. Okay, perplexity is a measure. If you build a language model and you have a test set that was not part of the training, then higher perplexity is just better, because higher perplexity would mean that lower perplexity will be better because it sort of corresponds to a loss. So what we need a loss function to evaluate intrinsically, right? So these models are issuing probabilistic forecasts of which word is coming next. So we can use any loss function from the probabilistic forecasting literature, and a very, very standard loss function is log loss, okay? Log of the inverse probability of the next word, right? So if I say that the next word is talking with probability 0.99 and the word turns out to be walking, well, I made a horrible prediction, right? I was almost certain that talking is going to come, but in fact, I saw walking, right? So that would be a bad case. So it's the log of 1 over the probability of the word that actually occurs in the test data, and the probability is computed according to your trained model, right? So your model should assign higher probabilities to what actually happens. And so if you take a very long sequence, if you have a very, very long corpus and you just join it using sentence separators, you can consider the sentence separator itself as a token, and you can compute this average log loss. There's a minus sign in front because I really want log of 1 over the probability. And I want higher probabilities, right? So I want this loss to be smaller. And the average log loss is kind of a measure of how much uncertainty there is in bits, right? So if you are saying that I always have next outcomes and they're all equiprobable, then this loss will tend to be about log v, right? Because your probability will be 1 over v, and so minus log of that would be just log v. In NLP evaluation metrics, they often say 2 to the power this log loss, and that's what they call perplexity. So perplexity is just 2 to the power of this average log loss. And perplexity itself has the interpretation of like sort of the average branching factor, right? So if you knew nothing about your language, if you didn't capture any statistical regularities, and your language had a vocabulary size V, and if you were equiprobable on that size V set, then your perplexity would be V. But if you've captured a lot of regularity and you say that, well, English has 100,000 words in its vocabulary, but at any given point in time, given the prefix, I am pretty certain that the next word is going to be within one of these 100 probabilities, right? Then the perplexity would drop from 100,000 to just 100, okay? And that's the conversion, that there's a log factor conversion between log loss and perplexity. So in this uniform case over V possibilities, you're expecting to see a log loss of about log V, but the perplexity will actually be V because perplexity is 2 to the power log loss, okay? And I'll come back to perplexity just for a second towards the end of the talk. So word embeddings, okay? So word embeddings will allow us to capture some aspect of meaning of words. Now, why do we want vectors? Because neural networks, the only thing they know how to operate on are vectors. That's all they know, okay? So we have to translate words into vectors. There's one very easy way to translate words into vectors, which is just use the one-hot encoding, right? So list your words in the vocabulary in dictionary order. The first word gets a vector which is 1 in the first place, followed by zeros. The second word in the dictionary gets assigned the vector 0 followed by 1, and then all zeros, and so on and so forth, right? So you just shift the position of the 1 to the index corresponding to the word in some fixed order, maybe dictionary order. What's the problem? Well, the good thing is you got your vector representation of a word. The bad thing is it has no idea about meaning. Every word is the same distance from every other word. So synonyms are as apart from each other as completely unrelated words. So it's a word embedding, but it's not very useful. So how do we make our word embeddings more useful? We want to capture meaning. We want to have words with similar meaning to actually have similar vectors. How are we going to get these similarity judgments? One idea is to ask human subjects, right? So you can show pairs of words to human subjects and say, what do you think? Are these words similar or not? And maybe you get some numerical score, and then you try and come up with an embedding that respects the human similarity judgments. Now, of course, the problem is who is going to answer, right? You'll have to recruit lots and lots of human subjects to get these labeled similarity judgments. And on top of that, there might be disagreements and heterogeneity in human responses. So this approach, while it kind of makes sense, is probably not going to scale. So the key idea behind word embeddings is, well, let's just not ask humans for similarity judgments. Why can't we use text generated from humans itself? Maybe there is some signal there about similarity that's already there, and we don't have to ask humans about how similar two words are. And this hypothesis, called the distributional hypothesis, which was first articulated by linguists in the 1950s, this is the central concept underpinning word embeddings, right? The idea is that if two words are synonymous, if A and B are synonymous words, they will occur in almost identical environments if you collect a lot of data, right? So if eye doctor and oculist, they're almost synonyms, and you look at context in which an eye doctor and oculist occurs, you will see similar context around it. Now, it seems hopelessly recursive because you will say, well, I'm trying to find the word embedding of a word. I'm supposed to find out what occurs around them. And if that's similar, then these two words are similar. But what occurs around them are also different words whose word embeddings I don't know. So isn't this an infinite regress and I will never come out of it? And the answer is no. And we will soon see, because what we do is we will use these as constraints on our embeddings. And then these constraints are, if they're tight enough, we will get an interesting embedding out of by just introducing these constraints that if two words co-occur a lot, then their embeddings should be similar. Because if they co-occur a lot, their meanings are similar. Okay, so this is a very sort of simple textbook type example drawn straight from an NLP textbook whose link I'll provide in the end. You can see so there's a distinction between a center word, right? The word that we're focusing on, and context words, the words that appear around it. So the columns here are center words, and the rows here are the rows here are center words, and the columns are indexed by surrounding context words. So if you look at fruit words, cherry and strawberry, context words like computer data and result don't tend to occur around cherry and strawberry. What tends to occur around cherry and strawberry? Things like pie, sugar. And if you look at center words like digital and information, then computer data and result do occur around digital and information, but then words like pie and sugar don't appear, right? So you're already seeing how if we do these word counts, we can try and get some aspect of meaning captured. And you can see this geometrically if you just think of embedding digital and information in a two-dimensional space, which just is represented by the counts for the word computer and data in their surrounding context. You can see that their vectors are pointing in almost the same direction, which captures the fact that data and computer, although they're not synonyms, they are clearly related words. Okay, so think of these word embeddings as not actually capturing synonyms or same meaning, but they capture more like related meaning, right? Are they just like that example of a bank and ATM and account? They don't mean the same thing, but they all talk about financial transactions, right? So they're clearly related. So this idea of the distributional hypothesis, sometimes it's also referred to as you will know a word by the company it keeps, right? So a word's meaning is somehow dependent on the meanings of the words that surround it in large text databases. So word2vec, this was a big advance in the field. This paper is from 2013. And here what the authors did was they came up with a very simple logistic type model for how to model the probability of co-occurrence, okay? So if W is a center word and C is a context word, I'll label it as a positive example. So this pair will be labeled as a positive example if I see this occurring together. And how do I define occurring together? I will choose a window of some fixed size, let's say 4 or 5, some small number, and then I'll look around all occurrences of the word W, and I'll see does the word C appear in the context around W, right? And what I will do is I'll create a logistic type model, that the probability that W and C have a positive label, naming that they actually occur together, is a logistic function of W transpose C. Okay, now in regular logistic regression, one of these is a parameter to be estimated, the other one is just given. But how it's different from regular logistic regression is that both W and C are to be estimated here. So usual logistic regression is a convex problem. This is not, because of this bilinear interaction, because we are trying to estimate both W and C from data. Now, how do I get my positive example? I just go out on the web and I look. Does the word W occur does the word C occur in the context around W? If it does, it becomes a positive example. It's a positive pair. How do I get negative examples? So this is another neat idea. Nobody explicitly gives you negative examples, but because only certain words co-occur with other words, you can just, if you look at any particular word and you start sampling words at random from your vocabulary, most of those pairs that you will get are going to be negative examples. So you get negative examples by just sampling at random. And in this paper, they said that for every positive example that you get from an actual data set, add maybe 5 or 6 negative examples by sampling. Okay, so you create a slightly imbalanced data set with negatives outnumbering the positives by a factor of something like 5 or 6. So then there are 2 main parameters of this method. How much do you oversample the negatives? That's one key parameter. And what is the window that defines co-occurrence? And those parameters are chosen by hyperparameter optimization. Okay, and another high-level view to understand what word2vec is doing is that intuitively what it's trying to do is, if 2 words are labeled as positive, it tries to learn their embeddings so that they are kind of pointing in the same direction. And if 2 words don't occur together, then it will pull them apart. Okay, and this is an idea behind a large family of representation learning methods that go by the name of contrastive divergence. So this word2vec is like a contrastive divergence representation learning algorithm for learning the representation of words. Okay, so I would like to spend most of the remaining time on transformers, so I'll just spend very little time on this third module in the talk, the neural language models. I believe that everyone at least has some basic familiarity with neural networks. So the basic computation unit in a neural network is basically a very simple nonlinear regression, right? So you say W transpose X, W is your trainable parameter or a vector to be estimated from data, X is your input, and you apply a single scalar nonlinearity to get your Y, okay? So this is kind of the basic building block of a neural network. And very common nonlinearities are, sigmoid was used very popularly in the classic literature. More modern papers use this piecewise linear nonlinearity called the rectified linear unit. You can also use the hyperbolic tangent. But the point is, if if you apply several different neurons on the same input, now you have a vector-to-vector mapping, right? So a single neuron computes a vector to scalar mapping. But if I just put several neurons in parallel operating on the same X, now I have a vector-to-vector mapping, right? Where the input dimensionality is the dimensionality of X, and the output dimensionality is the number of neurons I put together. And putting together neurons is called building a layer. And a layer computes a vector-to-vector mapping, which means you can now stack layers on layers, almost like Lego blocks, right? So if your original dimension was 10, and then the first layer computes dimension 5, then you can add another layer on top that takes that 5 to 3, and then maybe another layer on top that takes 3 to 1, and then eventually a scalar will come out from this 3-layer neural network, okay? So neural networks are just compositions of functions of the form sigma times a matrix Wi operating on an input vector X, okay? And because this is a matrix times a vector gives you a vector, so sigma applies entry-wise. You apply a nonlinearity entry-wise to each entry of Wi times X, okay? So that's a very broad picture of what neural networks do. A very key aspect for language modeling is that the very last layer is supposed to output a probability of words in the vocabulary. How do we do that? We just make sure that our last layer produces V real valued outputs. Now, these real valued outputs may be negative. They don't sum to 1. You force them to be non-negative, and the fact that they will sum to 1, which you need to output genuine probabilities by using the softmax function, right? So if I produce k numbers that are not guaranteed to be positive and they're not guaranteed to sum to 1, I can just exponentiate every one of them. So e to the z1, e to the z2, e to the zk. Now they're all non-negative. And I can divide by their sum. Now they're normalizing the sum to 1. So this little adding the softmax at the end is often called a language modeling head. And a head is a jargon for just a structured piece of the neural network that does something meaningful, right? So they use this word head a lot when describing various parts of a neural network. So language modeling head is a very simple object that just takes real valued inputs and produces a probability vector of the same size, which is very important in language modeling because the last thing you want to do in your neural network is exactly producing probabilities for what the next word is. So it's just a cartoon. Suppose you have a 3-order Markov model, but now I'm using word embedding. So I'm not using this one-hot embedding. So I embed for in some d-dimensional space. I embed all in some d-dimensional space. I embed the, and then these, usually the embedding is something like 300 or 500 dimensions is the typical size of word embeddings. You just concatenate all those word embeddings that goes into a neural network. And then eventually you produce V real numbers that are then softmax to produce V probabilities. And those are just to be interpreted as what's the probability of the next word, given that the last 3 words were for or the, okay? So this is now a neural language model. It is no longer this classical Markov model. We are not maintaining tables of probabilities. We are using word embeddings, and we are using a neural network to translate those word embeddings of words in my context window into probabilities for the next word. Okay. This idea of using a neural network as a language model was proposed by this very, very influential paper by Bengio et al. In 2003. And you can see these 2 distinct layers, the embedding layer that converts words into their word embeddings, and this language modeling layer that takes the output from the last layer of the neural network and computes probabilities. Here, the network has only one hidden layer, but you can stack 5, 6, 10, hundreds of layers, right? You can have lots and lots of layers in the middle, but what will stay constant is the embedding layer in the beginning to convert words into word embeddings, and a language modeling layer at the end to convert the output of the vector into probabilities over the vocabulary. And this embedding, you can either use something pre-trained like word2vec, or you can treat the embeddings themselves as trainable parameters and learn all of the trainable parameters in the network usually using some form of stochastic gradient descent. But again, I will not go into the training part because most of this talk is focused most on the architecture and the models. Now, okay, so I said that word embeddings will solve a problem. Do they solve it? Yes, they do. So what are the advantages of using a neural language model over these classic n-gram language models? So parameter count still increases with context length, right? So if you want 4 words to be part of your previous context, then of course the number of parameters in an initial layer will grow. It will grow linearly with how many words how many more words. So if it goes from 3 to 4 to 5 and 6, you will also have a linear increase in the number of parameters in just the first layer of your neural network, assuming that its output dimension is not scaling with the context window size. So parameter count still increases, but at least not exponentially. At least we are not encountering this v to the power n scaling. And more importantly, we can generalize to unseen word sequences. So here's a very interesting example, which I basically modeled after an example from a standard NLP book. Suppose in your training data, you saw the sentence, I fell asleep because the talk was boring. Okay? You've never seen this trigram. You've never seen in your training data, webinar was boring. Okay? You've never seen it. Now at test time, you encounter the following prefix. I found it hard to stay awake because the webinar was what? The neural network can predict boring because hopefully the embedding for webinar and talk are very close to each other. And also the embeddings of things like hard to stay awake and asleep are similar. So it can use that similarity to then say that, oh, actually boring is probably a likely completion of this, even though I've never saw the exact n-gram webinar was boring in the training data. Okay, so this is what word embeddings bring to the table. So the main point is that the similarity of the word talk and webinar as seen through the lens of these word embeddings will help the language model to predict boring, even though it never saw that exact trigram in the training data. Okay, so this is the most important part, the last part and the most important part. How many more minutes do I have, Himel? 5 more minutes?
5, yeah.
5 more minutes, yeah. So I should be able to get across the main intuition here. So this is, okay, so if you maybe didn't follow everything, that's okay. But this is a point to start paying attention again. So we saw that you can use neural models. But imagine a scenario where you're doing something like machine translation. So you want to take the embeddings of n words. Each embedding is d dimensions. And you want to transform these embeddings into another sequence. Okay, so you want to do some processing. You want to transform these embeddings because your original embeddings are just general embeddings. They are not aware of the actual context in which a word is found in a particular sentence. So maybe now that you have a particular sentence, you might want to modify those word embeddings so that after one layer of processing, you again have n d-dimensional embeddings, but now they're a little bit more informed by the actual context of which words are occurring around which words in my actual input. Okay, now if you just build a vanilla neural network, by doing this, the parameter count is going to scale as input dimension times output dimension. Both input and output dimensions are nd, so parameter count scales as nd square. And again, so you cannot use very large n's because you still have something increasing with n. It's not as bad as v to the n, but it's still n square. The beauty of the attention architecture is it completely eliminates any dependence on the n, the n-gram and the context window. Okay, so attention is going to be a neural network, one layer in a neural network where the total parameter count will be independent of how many words you allow in the context window, which then allows these models to become really, really big. You can process context windows in the thousands, right? 32,000 long context, 64,000 long context, which you absolutely cannot do with vanilla LLMs, Markov models. You cannot do that. You can also not do it with even with neural LLMs if you just have a vanilla architecture. So let's just see what's the magic behind attention that allows you to do this. And here I feel like if you read original papers, they use this vocabulary of databases. They use things like key query value, which I think is not very helpful if you're coming from a more statistical viewpoint. So the viewpoint I find helpful is viewing an attention as a trainable alternative to a simple nonlinear local smoothing regression method like Nadaraya-Watson kernel regression, which a lot of you have probably seen. So the idea is that if I'm doing, let's say, x's are vectors and y is, let's say, just scalars, so you're trying to just do a regression from vectors to scalars, you might say that for a test object with features covariates x test, my prediction for its y value is going to be some linear combination of the y values I've seen in my data set, but they're weighted by how similar x test is to each of the xi's in my training set, right? So if x test is very close to one of the xi's, I'll pay more attention to, I'll give higher weight to that particular yi. But if xi is very different from x test, then I will downweight it. Okay, so this kernel xi x test, k of xi x test, it sort of encodes this idea of attention or weighting of how much that part of the input is to be trusted, is to be used in producing the output. And the attention weights are usually designed to be non-negative and they sum to 1. However, in classic Nadaraya-Watson regression, the K is mostly chosen by the user. There might be a bandwidth parameter that you treat as a tuning parameter, but this functional form is mostly just chosen by the human design. And this is where attention changes things. So what attention does is it introduces trainable parameters into this kernel sitting inside the Nadaraya-Watson idea. Okay, so let's say we introduce matrices. These matrices will be of size d by d if you're using a word embedding dimension d. WK and WQ, this is because of this whole key query value terminology. You can ignore the subscripts here. You just say that I have one matrix WK that transforms Xi and another matrix WQ that transforms Xtest. And this is going to be my working model for the kernel I will use. This is no longer a fixed kernel because I have these trainable matrices that can get trained by backpropagation in SGD if I have some target loss, like the log loss, right? So log loss can be used to evaluate LLMs. It can also be used to train LLMs. In fact, that is the most commonly used training loss, the log loss or cross entropy. Now, the self in attention refers to the fact that there is in regression, there's a distinction between X's and Y's, right? The inputs and the outputs, the covariates and the responses. But self-attention means that a sentence you look at the sentence itself to output the next layer representations of each word in the sentence, okay? So think of Xtest as just one of the input words, Xj, in particular, the embedding of the jth input word. And Ytest is going to be the transformed contextual embedding of word J, but now on the output side, okay? So in regular regression, I only have to output one Y value. But now if I have a sentence of length n, I have to do this n times over, but I can do it in parallel, which is one of the strengths of attention, that the computation across words in a sentence is completely parallel because I use the same exact attention operation in parallel over the n words. Okay, but if I zoom into one particular word, X prime, the prime here denotes that this is now a transformed embedding of word J. This is now exactly the Nadaraya-Watson form, except that the kernel has now become trainable, and I've added another learnable parameter WV, it's hitting Xi, right? But other than that, it really has the same form as Nadaraya-Watson kernel regression. Now, you might say that, well, these inner products can be negative and they don't sum to 1, but that's an easy fix, right? We can use softmax. So we just softmax these values to get our requirement that the attention weights have to be probability vectors. Key thing, and I'm almost done with my talk, the key thing is that all learning matrices now are d by d with absolutely no dependence on n, right? So whether I'm doing a context window of 3 or 4 or 300, I always just have to learn order d square parameters in one layer. And typically you will stack maybe 96 such layers, okay, to get to a transformer. So what I described to you is self-attention. I'll skip the intuition because I'm running out of time, but if somebody has a question, I can give this intuition. Just want to end the talk by saying that, so self-attention can be thought of as a trainable version of Nadaraya-Watson regression. And if you stack many such self-attention layers with a few bells and whistles that we don't have to go into, then you get a transformer. So a transformer is basically just a stacked neural network consisting of lots and lots of self-attention layers. But other than that, it operates just like the neural language model. You get your words, you have a very deep architecture consisting of self-attention layers that outputs next word probabilities. You generate a word from that, you add it, and then you generate again, you add it, and then you generate again. So this is called autoregressive sampling. And that's how GPT models produce these coherent long sentences in response to a prompt. And the prompt is just used as the initial conditioning, right? So the answer is just drawn as conditioning on the prompt and drawing more and more words. So yeah, so I mentioned perplexity. Huge gains in perplexity. If you use Markov models, it's very hard to go below 100. GPT-3 achieves, on a very standard benchmark, achieves a perplexity of 20.5. Huge drop, right? So that's why we call it a revolution. There are many open questions. Again, I'm happy to take questions if people are interested in hallucinations or skills or scaling. But I'll end the main talk by thanking all of you for coming. And if you want more details and all of my images, so image credits to this very nice book being written right now. And if you have the talk slides, This will take you to the link of the book, Speech and Language Processing by Jurowski and Martin. They're writing the 3rd edition. And the Nadaraya Watson view of self-attention, I borrowed it from Dive into Deep Learning by a bunch of folks at Amazon. Thank you.
Yeah, thank you, Dr. Tewari. It looks like we have 3 questions in the Q&A, 4 questions now, maybe 5 by the time we are looking at it. Can you see the questions? Just wanted to make sure, Dr. Tewari, because there are some equations that might be easier to read. If you go to QA.
Oh, QA. I was looking at the chat. Sorry. Yeah. Okay.
And there are 5 open questions. So we can start with the first one.
Yeah. So how is the test data selected? Is it the entire set, or we evaluate on a set of such text collections and take the average? So you can think of the test data as, so in reality, the test data would be many, many sentences drawn from, let's say Wikipedia, Reddit. In fact, you crawl the whole web and you should then set aside part of it for testing. And you can use a simple trick that if you include in your vocabulary, one of your tokens in your vocabulary. So I was behaving as if vocabulary is just the word. In practice, words are not the units. You use subword tokenization and they become your tokens on which the transformer works. So one of your tokens can simply be a sentence separator. So part of what you're learning to model a language is you're also learning how to model the ending of a sentence. Right? So then it is just fine to just concatenate everything in the test set into one long mega sentence and just compute the average log loss on that super long sentence. So that was the first one. Second question is, so the embedding layer is basically the output of logistic regression using positive and negative cases. Yes. Okay, so again, I want to emphasize that when you use a large language model, the embedding layer could use embeddings of 2 different types. You can either use a pre-trained embedding, could be word-to-vec, or you can just treat the embeddings themselves. An embedding is just one d-length vector for each token in your vocabulary. Those are just parameters. They can also be learned when you do end-to-end training of your entire network. But yes, when you do use word-to-vec, then essentially you're using a logistic regression type, sort of a maximum likelihood on a logistic regression loss function to learn the embeddings of WNC. That is the central insight of word-to-vec. Vanilla neural network needs order ND square parameters. Why is that? So, okay, again, let me just explain. It's not always the case, right? So if you are doing sequence-to-sequence transformations of a sentence containing n words, each word has embedding dimension D, and you want to preserve the embedding dimension on the output side, then n times d numbers have to be transformed into n times d numbers. And the scaling of the number of trainable parameters in a vanilla neural network layer, also called fully connected layer or a dense layer, the scaling is input dimension times output dimension. So if your input dimension is nd, your output dimension is nd, then the scaling is n squared d squared. There's one more question from Srijit Mukherjee. Okay, I like the fact that you like the Nadaraya Watson intuition. I think it's the right intuition for a statistical audience. I don't think the key query value thing is really just a distraction. I think it helps people who have a database background. So I really appreciate your comment that you like the Nadaraya Watson intuition. Now there are questions from slides 16 and 17. So let me go back. Okay, so slide 16, how are the counts done for identical environments in digital information in terms of computer and data? Do we use cosine similarity? Yeah, okay, so there are 2 different questions. One is about the similarity on the slide 17, and then the other is how do we compute these counts? So these counts are computed by fixing a particular corpus. And which corpus do you use depends on your end goal. If you're building a very restricted system, maybe you only use a corpus of newspaper articles if your idea is to only build a language model for sort of journalism, right? But these days, language models are built for general purpose use. So they are trained on sort of the entire internet and all the books ever written, right? So they basically just digest everything. And then the idea behind building a matrix like this is that for any word like digital, you look into your entire corpus. Wherever the word digital appears, you look maybe 4 words into the future, 4 words in the past, forward and backward, and you just say how many times did the word computer occur within 4 words of digital, and you put that count there, right? So building these count matrices is of course, if you do it at scale, it can be slow, but there are efficient techniques for building these counts very fast. And then in terms of which metric to use, so cosine similarity is the most common one, but you can really use any notion of similarity on vectors. But yeah, but cosine similarity is a very, very, very commonly used way to, once you've trained embeddings, you can look at the cosine similarity and then try to maybe calibrate it against human notions of similarity to evaluate. So you don't want to train your embeddings on human input because it doesn't scale, but you can always evaluate. You can say, does word-to-vec capture the same similarity if you ask human subjects? And then you can use the cosine similarity coming from word-to-vec with human similarity judgments to see how much they align. There's a question, very general question about how should we get into this space? And I'm assuming the space referred to is just sort of transformers and LLMs. I think that a very good introductory deep learning book, which is very modern, will spend a lot of time discussing transformer because just it's been so influential. So the Dive into Deep Learning book has several chapters on attention and language modeling. And then I think it also makes sense to read up a little bit of the history of natural language processing. So this progression that I said, simple Markov models, then word embeddings, then neural models, then these large language models, credit is due to this Murjaratsky and Martin book. They have chapter sequence like this. And all I've really done is I've taken those chapters, condensed them to make the 4 modules of the talk. So if you want to learn more, I would say start with these 2. And then, of course, there's no limit, right? Because you could go in many different directions.
All right, I think we are just 11. So we're, I think, ready to wrap up. Maybe Dr. Banerjee.
Yeah, hi. Thank you. Thank you, Dr. Tewari. This is like, very fascinating talk. And I'm sure, all of us learned something today, like out of this talk. And I really appreciate to you to come here and, to give this webinar to educate, like, our statistical society overall. And besides that, I want to thank, like, all the participants who joined today. And like, it's such a great, audience today. Like, I really want to thank all of you. And especially I want to thank like the whole webinar committee, like who are putting a lot of effort together to make this type of webinar happening every month. So I want to see, you guys again, like in the next webinar, we actually post all our information through our LinkedIn page. And especially for this talk, we will be like, sending out like, LinkedIn post where we will be putting like, the recording and like slides, etc. And thanks again, like, for doing this one, Dr. Tewari.
My pleasure. Thank you so much for having me.
Right.
Thank you. Bye.